Okay. Okay. So, hi all. Very good evening, and welcome back to the fourth week of live sessions for artificial intelligence search methods for problem solving. So, can anyone first confirm whether the screen is visible or is my voice audible? Thank you. Thanks for confirming. Okay. So, this week we'll be covering some questions, some practice questions related to week 4 content, which basically dives deeper into stochastic search methods, uh, things like genetic algorithm and how we can use it to solve the TSP or the traveling salesman problem. And through these questions, I hope we'll familiarize ourselves with some nuances that will help you solve the upcoming assignments. Okay, so before we start, does anyone have uh, anything to share or any specific issue that they would like to bring up? Okay, that's great. So let's move ahead with the questions and then yeah, we'll see if there are any specific doubts or explanations needed. Okay, so let's get started. So this is the first question in front of you. Maybe I'll zoom in a bit. Okay, so there's a graph shown on the left hand side over here, which is basically a graph that depicts a closed ecosystem. Okay, so these arrows basically suggest that a certain entity directly influences another entity, directly or indirectly influences another entity. Okay, so for example, consider this a box called grass over here. Okay, so grass has a direct edge or an arrow from grass to grasshopper, and then it also has an arrow from grass to mouse and from grass to beetle, which basically what that means is that grass directly influences grasshopper, beetle, and mouse. Then mouse in turn directly influences snake. Okay. Similarly, if two boxes are not connected directly via one arrow, but through a series of arrows or edges, then you could say that they have an indirect influence among themselves. Okay, so that is the setting over here basically. And based on this graph, you have to choose among the options that are provided on the right hand side over here. So I'll let you go through the uh, graph and the options, and then we can have a discussion on which of these are true or which of these could be concluded to be true based on this given graph. Yeah, thanks for your question, Rocky. So, uh, positive influence basically here. So, here we are talking about positive influence alone. Okay, so there could be something like negative influence, but we are not considering that as of now. So basically, if we just think about this in terms of an ecosystem, we could say that grass basically helps mouse and grasshopper and beetle survive. Okay, in turn, grasshopper helps sparrow survive. Sparrow in turn helps snake and hawk survive, and hawk in turn helps the fungi survive. And fungi in turn helps the wildflower survive, and so on and so forth. So all these things are having a positive effect on the other entity. That's why we call this a positive influence. You could have another setting where things could be interpreted as having a negative influence, but that is not what we are concerned with in this graph. Uh, does that address your query, Rocky? Okay, great. So you can take your time and Once you are comfortable with a set of answers that you think would be true in this case, you can feel free to write it in the chat box, or you can unmute yourself as well and speak up. Sure, Lekana, thanks for your question. So basically, what we are considering over here is an ecosystem. Okay. Uh, so what basically this depicts is an influence graph, which basically means what influence, or we are considering positive influences only over here. Uh, one entity is having on another entity. Let's say we consider this bacteria. Okay. Let me just shift to my Jamboard. Let's say we have some entity, bacteria. Now, what the graph over here is telling, that this bacteria is having a positive influence on trees and carrot and grass. Okay, which basically could be interpreted as this bacteria is helping the other entities survive in the ecosystem. How that is possible? That you could draw that from your high school biology knowledge, that maybe a bacteria is helping a carrot plant grow, it's helping a tree grow, and it's also helping grasses grow. So you can say that it's having a positive influence on these particular entities. Okay, so this is a very hypothetical example. Okay, don't take it to heart. This is just to study the uh, reduction pattern, or how can we reduce the influences, direct and indirect influences from a given graph. Okay, now let's say carrot in turn influences another entity. Okay, let's see what is there in the graph. Yeah, so we have an entity called a rabbit over here. Let's say rabbit eats on the carrot to survive. Okay, to survive in the ecosystem, and carrot in turn takes the help of bacteria. So bacteria is having a positive influence on carrot, and carrot is having a positive influence on rabbit. So you could say that bacteria is indirectly influencing the rabbit. So it would be better if I show this with let's say dotted edges, which is that bacteria is influencing rabbit in a positive way through the carrot. Okay, so this is what this is basically. uh, I hope that addresses your query. Okay, that's great. Again, good question, Hina. So there could be another instance, another problem, or another graph where we could have something like a negative influence. Say the existence of one species is causing the uh, extinction of another species. Okay, take a hypothetical example. Okay, suppose there is one animal who is let's take the example of us humans itself. Okay, suppose there is a hypothetical or imaginary farmland, okay, or a forest where a lot of animals and species used to live, and some humans come there and they decide to cut down the forest. Okay, so that will negatively affect the ecosystem or the survival of the other species or animals that had already been living in that forest. So that could be an example of a negative influence. Okay, but that is again a hypothetical example. Don't get too worried about it. In this example, we are only talking about positive influences. Um, I hope that addresses your query. Yeah, Rocky. So the question is based on true or false. So basically, among the options provided here on the right hand side of the slide, you have to select which of these we can successfully deduce or conclude based on the graph. And to address Bharadwaj's query, you can find the I'm not sure about what do you mean by assignment recording sessions. I'm not sure whether we have anything like that, but the live session recordings that you can find if you go to the Swayam portal. Uh, okay, you mean the current session. The current session is being recorded right now. And once we have completed today's session, I will be uploading it on the YouTube channel where we usually upload all the videos. So it's there through that channel that you can access it. Okay, so maybe let's go through the options one by one, and that will help us narrow down our answers. So the first statement over here says that grass has a direct positive influence on lions. So what do you think about that? Okay, so some of you are saying that it is false. Um, Okay, quite a few of you are saying that it is false, and that is in fact correct because there is no direct connection or direct arrow between the grass entity and the lion entity. Okay. Okay. So to address another question regarding the YouTube channel link, so if you go to the Swayam portal, I'll just show you once. Just go to this section over here called problem solving session recording. Okay, this will take you to something like this. If you use this click here link, you will be able to access all links to all YouTube channels, the slide folder, everything is there. Okay. Okay, so we concluded that the first statement is false. Okay, now let's consider the next sentence. Grass has indirect positive influence on lions. So what do you think about this? Correct. Yeah, as many of you say, this is in fact true. Uh, what about the third statement? Bacteria has a direct positive influence on fungi. That's right. Again, false because there is no direct edge connecting bacteria and fungi. So there is one edge connecting bacteria and fungi, but the direction of that arrow is from fungi to bacteria. So fungi is having a direct influence on bacteria, not the other way around. So that's why we have to say that this is false. Okay, what about the fourth statement? Bacteria has an indirect positive influence on fungi. Yeah, that is true. Because so if you follow this direction or this path of arrows, from bacteria you go to trees, from trees you go to beetle you go to robin you go to hawk, and then from hawk you go back to fungi, right? So we have this path from bacteria to fungi through some intermediate entities or nodes, right? So we can say that there is an indirect positive influence from bacteria to fungi. Okay. um, So there was a hand raise in the in between, which got which disappeared after a while. So If that was by mistake, that's fine. But if that was on purpose, please feel free to unmute yourself or write your query in the chat box. Okay, let's consider the other statements now. So the other statement is hawk has a direct positive influence on fungi, which is true because we have a direct edge from directed from hawk to fungi. And then hawk has only indirect positive influence on fungi. That is, what do you think about that? Yeah, that is false because hawk has direct influence on fungi. We just saw that. And what about the last statement? There is at least one node in the graph that is not influenced by any other node. Right, so this is false as well. There is no such node in the graph that is so the statement basically there is at least one node in the graph that is not influenced by any other node. That is not true. Let's check our answers. And as we saw, the three of the statements that we deduced to be true are actually correct. So this was a pretty straightforward question and just application. Um, uh, any doubts? Sorry about that. Any doubts on this question? Okay, that's great. Thanks for your answers, all of you. Okay, now let's move ahead to the second question, is which is not as straightforward as the previous one, but still it's a fun problem to solve. Okay, so how many of you um, remember the or have watched the videos about the genetic algorithm that is covered in the week 4 content? Okay, great. So we have one thumbs up. We have another confirmation in the chat box. That's great. Many of you have watched it, so that's great. So what I will just do a quick review of what that was. We start with an initial population. Okay. uh, okay, we generally have to solve some kind of an optimization problem over here. Okay, so we start with an initial population of candidate solutions. And what we do is then we use some measure to evaluate the fitness of those initial candidate solutions. Okay, so basically we'll assign a function that will tell us how well suited this particular candidate solution is to finally optimize our bigger problem. And based on a few conditions, we will try to change or modify our population, the initial population, so that we get the next generation of candidate solutions. And how we do that? That we do through the operations of selection and crossover. Okay, and optionally something called mutation as well. And then we iteratively keep on changing the or modifying the solutions in generation after generation until we reach a particular stopping or termination criteria, or until our optimization, that is minimization or maximization uh, uh, problem has been solved. Okay, so that's a good question, Rocky. How is the fitness function determined? So that actually depends on the problem that you're trying to solve. So depending on the problem, the fitness function could be as simple as something that is shown over here in this example or in this question, or it could be something very complicated as well. Okay, so it basically depends upon the problem that you're trying to solve. Okay, so I'll just go through the question over here. So we are given some 5-bit binary strings, okay, which are these 10010 strings, and we are giving a fitness function or a cost function that is a function of these individual bits A, B, C, D, and E. Okay, so A, B, C, D, E basically represents the bits at each of the 5 positions of the 5-bit binary string. And the fitness function is defined as the square of this A plus 2B plus 3C plus 4D plus 5E. Okay. Okay, so I think there was some glitch at my end. Were you able to hear what I was saying just now? Okay, that's great. That's great. Okay, yeah. So that is how we evaluate the fitness of each individual or each candidate solution. And what we have to do is we have to basically fill in this box, this table over here, to decide which values or which of these candidate solutions are moving on for the selection and crossover operations to obtain our next generation. Okay. So basically what we have to do is, so I'll just quickly go over what this table implies. Um, so initial ABCD is the initial set of candidate solutions that is given to us. Okay, so let's say the first individual or person in our population is 10010. The second candidate or individual is 01001. The third individual is 00101, and the fourth is 01111. Okay, so we have 4 individuals to begin with. Now, what we have to do in the second column is this F, A, B, C, D, E. We have to evaluate the fitness of each of these individuals based on this function that was given to us. Once we have this fitness, we have to find out the probability, okay? Probability of selection of each of these individuals, okay? So I'll give you a hint till then, and I'll give you some 5 minutes or so that you can try to solve this on your own, and then we can have a discussion on uh, the actual solution. Also, you are given the freedom to assume that the actual candidates selected are proportional to the expected number. Okay. And what you have to find is basically is the last column is this value of this capital A, capital B, capital C, and capital D, which basically means that how many copies of each individual are you going to move ahead to the next generation for selection and further crossover and so on and so forth. Okay, and since there are 4 individuals, these values of these capital A, B, C, and D can range from 0 to 4. As in, you can either select 0 copies of a certain individual from your current population, or you could select 1 copy, or you could select 2 or 3 or 4 copies. Okay. But remember that the sum of A plus B plus C plus D, that is the capital A plus B plus C plus D, has to be same as 4. Okay, so you cannot select more individuals than what you have in the current population. Okay, the number of individuals in the population has to remain 4 because you began with that. Okay, I'll let you solve this, and then we can have a discussion. Okay, so I see that many of you have already shared the solution to the first column, and some of you have also shared the full solution, and that's great. But we have to check whether the solutions are correct or not. So now let's start solving the columns one by one. Okay, so let's shift to our Jamboard. So let me enlarge this a bit. Is this clearly visible, or should I zoom in further? Okay, great. All right, so let us write down the fitness function that is given to us. Okay, we have a plus 2b 3c 4d and 5e. Okay, and so computing this particular fitness function is pretty straightforward. You just plug in the values of these small a, b, c, d, and e, and then you square it. Okay, so for example, the first one has a 1 in the a position and the d position, right? So this one will have 1 1 and all others will be 0. So the sum would essentially be 1 plus 4 or 5 squared, which is 25. Similarly, as many of you have said, the second one will be 49. The third one will be 64 and then 196. So let's just write that down. Okay, so that's great. So for the next step now, okay, sure, no worries. Let's quickly go over this once more. So you got how we got 25. Did you get
Yes,
how
sir.
we arrived at 25, or did
No,
you
sir.
find that a bit uh, strange? Okay, maybe let's go over the second candidate solution, and maybe that will help it clarify it. Okay, so let me erase this particular thing and write down the second candidate solution over here. Okay, so second candidate solution is 0 1 0 0 1. Okay, 0 1 0 0 1. What this basically means is that small a has value 0, small b has value 1, small c has value 0, small d has value 0, and small e has value 1. Now you just put these values into our equation. Okay, so a will be equal to 0. This, since b is 1, this will evaluate to 2. Since c is 0, this will evaluate to 0. Since d is 0, this will evaluate to 0. And since e is 1, this will evaluate to 5. Okay, so the sum becomes basically, this whole thing becomes 2 plus 5 squared, which is 7 squared, which is 49. Okay, okay, that's great. So yeah, we'll arrive at the formula for the expected value. Don't worry about that. Uh, why isn't 0 1 2 3 4 considered? So what do you mean by that? Uh, can you elaborate on your question? Yeah, sure, no worries. We will get to the probability column. We have not yet started it. Uh, okay, but let's go ahead with it. In the meantime, Vipu, you can maybe write down your doubt in a more elaborate fashion, and then we can address that. And also thanks, Sandhya, for uh, sharing your insights on the expected value. We'll get to that. Is the range supposed to be multiplied or the binary input? So which range are you exactly referring to over here? As of now, we are not doing any kind of multiplication. We'll come to that when we are supposed to find the expected value. And yeah, let's proceed with the solution, and then maybe we can come back to your question. Um, okay, yeah. So now that we have found the fitness value of each of these candidates, let's quickly find the sum of all of these. Okay, and if I remember, it is supposed to be something like 334. Can any of you just quickly confirm whether that is the sum? Okay. Okay, great. What is crossover? We will get to that. Don't worry. Let's slowly move ahead through this example, and by the end of it, hopefully, you will understand what that is. Okay, so that is 334. And so this also asks you to calculate the average, which is not really required, but you can still calculate it and you can keep the number for yourself. Um, okay, so basically, now we have to calculate the probability of each of these. Okay. And how you are going to do that is by dividing this fitness function of each individual by the sum. Okay, so the probability for this first individual, let's give a name to all of these. Okay, let's call this one as number 1. Let's call this as number 2. Let's call this as number 3. And this one as number 4. Okay, so the probability of number 1 will be the fitness value divided by the sum of all the fitness values of all the candidate solutions. Okay, so can someone quickly tell me what this value is? Okay, thanks Ram. So Ram has already calculated these values. So yeah, so we have 0.07. So let's write that down. 0.07. Then we have 0.146, which I guess we can round it off and write it as 0.15, or let's just go with 146, even doesn't matter. In that case, let's just write it as 0.074 as well. And 0.19 and 0.586. Okay, and if you quickly do a very double checking, you'll see that the sum of all this probability is coming to 1. Okay. Now, can anyone tell me intuitively what exactly is this probability representing? So basically, our objective is that we want to select some of these individuals from the current population. Okay, so we want to select either number 1, number 2, number 3, number 4, and create multiple copies of them so that we can use those as the parent copies and generate new individuals for our next generation. Okay, so basically the process, if we write it as a flow chart, would be something like this. Okay, so we have some initial population to begin with. Okay, then we do some kind of a selection to arrive at a newer population, which is an intermediate population, let's say. Okay, I'm not writing the whole thing. It's an intermediate population. Let's say there are 4 individuals over here because we started with an initial population size of 4. Okay, so we're going to maintain that, and then we are going to basically select some of these. Okay, so I'm selecting top two and bottom two. This can vary depending upon your selection procedure, and you're going to use these two to generate newer solutions. Okay, or newer candidate solutions. And this can act, so there are n number of ways to do these kind of things. There are some examples where you simply copy an individual from a previous generation to the next generation. There are some examples where you do a kind of a crossover, which we will get to in a while, to generate new solutions, and so on and so forth. So I'll quickly remove these things. What we want to do is we want to quantify uh, how likely each of these individuals from the current population is to move ahead to the next population. Okay, and if you remember something like survival of the fittest, from the concept of Charles Darwin, the theory of evolution, what that means is that the higher the fitness of an individual, which in this case is represented by these numbers over here, the higher the fitness, the more chance it has to survive, which is basically means to move to the next generation. Okay, so if you basically imagine something like a wheel, okay, let's imagine there is a wheel which is made up of four segments, okay, and each of these segment represents the probability for each of these individuals. Okay, something like this. Okay, let's say this is the probability of individual 1, 2, 3, and 4. Okay, this might not exactly depict the values over here. For example, here 0.586, which is the probability of the fourth individual, as the highest value. So the corresponding area of the wheel given to this particular individual would be the highest. Okay, let me just write that down. So this would be 4. Maybe the smallest one would be 1. Okay, and then something like this, something hypothetical like this. Now suppose there is a marker over here hanging at the top of the wheel. Okay, and now you rotate this wheel, give a random swirl to this wheel. So after this wheel has stopped running, it will the marker will basically land at some point, right? Suppose after stopping, this marker landed at the segment 4. Okay, the orientation of the wheel changed and the marker stopped at the segment 4, which means that you will select the fourth individual, and the higher the probability, the higher the chance it is for the marker to fall in that segment, right? So if let's say we have a wheel where half of it is given to one segment and the other halves are all divided into small segments. Okay, so when you rotate this wheel, this particular area will have a higher chance of stop of getting basically the marker being falling in this particular area, right? Just because it has the higher area or higher segment area. Okay, so that is the intuition behind why we calculate the probability in this way. Okay, so that was just an intuition. Let me remove all this. Um, so is it clear basically how we arrived at this probability, the values? Okay, great. Uh, okay, no worries about the interruption. Um, Whether we need to find the binary value for the initial ABCDE or any other, please clear the steps, sir. So you don't need to find the binary value. You are already given the solutions in this binary format. Okay, so this is one hypothetical problem where your solutions, candidate solutions, are binary strings themselves. You can have another problem where the solution would be of some other form, but in this particular problem, you are only concerned with binary strings. Okay, so you don't need to find it from anywhere, that is given to you. You have to modify it if you are required to proceed to the selection and crossover steps of your algorithm to arrive at the next and the upcoming generations of solutions. Okay, I hope that addresses your query. And now coming back to our question. So if you remember, I had told that we can make an assumption that the actual candidates selected are proportional to the expected number. What this basically corresponds to is we just talked about of the wheel of selection, right? So since we have four individuals, we will rotate that wheel four times to select four individuals, and because uh, in order to find the expected number, we will basically have to multiply the probability by the number of individuals in the population or the number of times we are rotating the wheel. Okay, because that many times is the chance for that individual getting selected. So this will basically be 0.074 into 4. Okay, can anyone tell me what that is? Okay, 0.28, 0.56. Let me just write that down. 0.28, 0.56, 0.76 and 2.32. Sorry about that. Okay, so we have arrived at the expected value. Okay, and now we see that the fourth individual has the highest expected value, which is 2.32. Okay, and the other individuals have somewhat comparable. So these two individuals, which is the second and the third individual, have somewhat comparable expected value. Okay, 0.5 and 0.7, which is very close. So what we are going to do is, and uh, the first individual has a very low expected value in comparison to the others. Now, in our next generation, we want four individuals, right? So what we are going to do is, since the expected number of this fourth individual is the highest, we are going to have two copies of this one and one copy of each of these second and third individuals, and no copies of the first individual. What that basically means is that the first individual was not fit enough to move on to the next generation, so this particular is discarded. Maybe I shouldn't put the cross mark over here. This is discarded. One of uh, these individuals is moved on, one of these individuals is moved on, and two of these is moved on. If I have to write that down, so our initial population was 10010 and 01001 and 00101 and 0111. This was our initial population, and after all this trouble that we went through, what we are going to have is, we are not going to have any copies of this particular individual. We are going to have one copy of this individual. Okay, so we're going to have 01001. We are going to have one copy of this individual, 00101, and we are going to have two copies of the last individual. So this is what our next generation would look like basically. And then we can perform further selection and crossover among these to arrive at a modified version of this. Okay. Um, okay, so a couple of questions in the chat box. Let me just address them one by one. Um, so Dr. Ashwini, I would be glad to discuss it if we have time remaining, but I would suggest that if you have some specific topic in mind that you would like uh, to be discussed in the coming live sessions, let's say from going forward, uh, it would be better if you give me some 1 or 2 days in advance, right? Um, let's just say that you post in the discussion forum saying that you would like this topic to be discussed in the live session, and so I can also prepare beforehand, because see, all of us are busy, so It's good if we have some time, if we're able to give some time to prepare beforehand, so that becomes the process becomes efficient for everyone. But anyway, I'm deviating from the point. If we have time, we would discuss that. Okay. Okay. Uh, on I suppose you meant to write on what basis the number of times a candidate is selected. So we just explained that it's based on the expected value. Okay, and then we have, is there any formula for finding actual from expected instead of just calculating by looking at the numbers? So no, there is no specific formula. So usually we work with toy examples in this course. So there the uh, process of arrival from expected to actual will be pretty straightforward, so you won't need to think too much about it. In actual application scenarios where you have to, let's say you're implementing this particular algorithm to solve some optimization problem, you can do something like setting up a threshold. If what that basically means is that if your expected value is less than a particular threshold, you will not carry that candidate forward to the next coming generations. If it is between a certain range, then you will carry one of those copies to the next generation. If it is greater than a certain value, then you will carry 2 copies of it or 3 copies of it, and so on and so forth. But yeah, there is no straightforward formula for calculating actual from expected. Okay, so expected column we basically got by multiplying the probability by the number of individuals in the population. Okay, so that's it. It's as straightforward as that. Okay. Okay, so a couple of you had asked about the expected value, how we got that. So that is basically, since we have 4 individuals in the population, we multiply the probability by that number. Okay, so if we had 10 individuals, you would have multiplied it by 10. If we had 100 individuals, you would have multiplied it by 100. Okay, so that is the basic intuition behind expectation, right? So if you go through any probability book, you will understand that pretty well. And as I was saying, there is no concrete formula to go from the expected to the actual number. It's more intuitive, and in the kind of examples that we'll be dealing with in this course and this exam based on this course, you will be having a very simple situations where it will be very evident how much or how many copies of an individual you should want to make or move ahead to the next generations. Okay, so don't need to worry too much about it. If you have some, as I was saying, if you want to apply it in some real world, then you can set some criteria. So one of the questions was, what is a threshold? A threshold is basically a limit that you set. Okay, so suppose your expected value is lesser than a particular pre-established or predetermined set value that you have decided, then you will not carry any copies of that individual to the coming generation. If it is greater than that value and lesser than a certain higher value, then you will carry one copy of that individual. If it is greater than a certain higher limit that you have set, if it is greater than that, then you will move ahead 2 or 3 copies of that individual. Okay, so that is something that you can decide. But in these problems that we are going to deal with, it is going to be pretty evident and straightforward. I hope that explains. What is the order of the final state? There is no particular order over here, um, but you can arrange them in the order of your fitness value if you want. Okay, so now that we devoted so much time, let's check the solution. And yeah, so we arrived at that solution. And you can take your own time to convince yourselves about or practice through this solution, and you can even change these initial population of A, B, C, D, E and try to find out or execute the same problem with different initializations, and so that you can familiarize yourself more with the process. Okay, so I'm assuming there are no further questions about this particular question. So let's move ahead to the next question now, which is kind of borrowing from this same question. We are just asked the individual instances selected for crossover are which of the following. Okay, so what this basically asks is what your next generation is going to look like, which we actually did discuss. Okay, so it's just going to be one copy of the second individual, one copy of the third individual, and two copies of the fourth individual. Okay, so it'll be looking something like this: one copy of the second individual, one copy of the third individual, and two copies of the fourth individual. Okay, so this is the answer to this question. Ah, nice question, Rocky. So if we have a hypothetical situation in which the probability is same for all, then with that basically means is if you connect this back to our rotating wheel intuition, this would basically means that all the segments have equal chance of getting selected, right? So basically what you will do is you'll end up randomly choosing one of them because all of them have equal chance. Okay, I hope that addresses your query. Okay, now let's move on to the next question. Okay, so I remember there was one question about um, what is a crossover, and we will arrive at that eventually in one of the questions, so please be patient. um, uh, in the meantime, this is the next question. I'll just address a few questions in the chat before coming to this question. Can we write 0 in the first place? You can write in the first place. That's up to you. Okay, basically that it's up to you because what strategy you want to adopt for your crossover operation, or your how you want to select the parents to generate the children for your next generation, right? So if you want to select the best solution and use the second best solution to generate the two children, then you can go ahead with that strategy. Or if you want, you can simply copy the best solution to the next generation straight away. The actual value for the situation would be 1111. So would there be a mutation? So mutation is a optional step in this whole process. Okay, so for some problems you are required to do mutation, for some problems you are not required to do mutation. In this particular problem, we were not told anything about mutation, so we are not going to worry about that. But if it is required in some hypothetical situation, what you could do is you could do something like you could randomly choose one of those bits of the 5-bit string that you had and just basically flip the value of that particular bit. Okay, so that would be corresponding to what a mutation would be in the real world scenario. Okay, so coming back to the fourth question that we have to discuss is, so this is now connecting back to our traveling salesman problem. Okay, so you are given four graphs. Okay, what you have to do is you have to find a tour that travels to it can start from any of these nodes. Okay, so the circles are the nodes and the lines are the edges. For each of these four graphs, you can start at any of the nodes and you have to travel through all nodes and arrive back at the same node that you started from. It's not necessary for you to cover all the edges, but what you need to worry about is covering all the vertices exactly once. Okay, so that is the definition of your traveling salesman problem basically. And sorry about that. In this question, what you have to decide is for which of these graphs A, B, C, and D is producing such a tour possible. Okay, and remember that you cannot make any new edge. You just have to travel along the edges that are given to you in the graph. Okay, so I'll again give you some 4 or 5 minutes to go through this uh, graph and try it out, and then we can discuss. Okay, so many of you have already shared the solutions, shared your solutions to this question, and many of you are correct. Some of you are slightly deviating from the correct solution, but that's fine. Let's have a discussion and see what will be the answer. Okay, so let's consider the first graph. Let's say you start from this particular vertex, you follow this edge, reach here, this reach here, this and this. Okay, so you were able to start from one of the vertices and cover all the other vertices and return back to where you started from. Similarly, in C, let's say you start from this vertex, you do something like this, and you come back. Okay, so in A, you were able to go through all the vertices exactly once and complete the tour. In C, you were able to go through all vertices and oh, okay. Yeah, I forgot to share the screen. Now it should be visible. So I'll just show it once more. No worries. Yeah, thanks for pointing that out to all of you. So basically what I was saying that suppose we start from this vertex, okay, and we move ahead in some direction like this, okay. So we were able to start from one of the vertices randomly and cover all the vertices exactly once and come back to where we started from. Similarly in C, we can start from here. We could do something like this, right? And once again, we were able to start from one of these vertices randomly and cover all the other vertices exactly once and come back to the starting point. But no matter how you try, how hard you try for B and D, you will not be able to go through all the vertices exactly once. There will be at least one vertex that you have to revisit in order to complete the tour for B and D. Hence, you cannot produce such a tour for B and D, but A and C can produce such a tour. Okay, so let's check the solutions. So as you can see that A and C have a tour, but P is getting stuck at one of the vertices. In order for it to complete the tour, it will have to revisit one of the other vertices that you had already visited once before. So that will break your condition of visiting every vertex exactly once. Okay, any doubts about this question? Okay, that's great. That's great. Then let's move ahead to the next question, which is basically okay. So now, till now, we saw how to apply genetic algorithms, and then we introduced ourselves to the traveling salesman problem. Okay, in the coming questions, what we are going to try to understand or try to figure is how we could apply the genetic algorithm to solve our traveling salesman problem. Okay, and one of the starting points for solving is to find the representation of the candidate solutions. Okay, and what is the solution in our case? A solution is a tour of the graph. Okay, so we are given a graph. We want to find a tour that goes through all the vertices exactly once. Okay, so it is, so what the candidate solution would look like is basically just a tour. Some of them would be going through the all the vertices exactly once and coming back to the point of starting, and that would be one of our solutions that we want to achieve. And some of these tours will not be satisfying that. Okay, so that is the starting point for us to find a proper representation of the candidate solutions. And sorry about that. One of the ways to do that is to through path representations. Okay, so basically this is a tour that is, it's a graph that is given to you, or a tour that is given to you of a particular graph that contains all these edges named P, Q, R, S up to Z. Okay, and among these options A, B, C, and D, you have to select which of these options are valid path representations of this particular tour. Okay, so again, I'll give you a couple of minutes to go through the solutions and then we can have a discussion. Oh, I see we already have a couple of solutions in the chat box. So let me do one thing. Let me just create a poll for this and you can share your answers over there. Okay, so many of you have uh, voted for the option of A and C, and that is great because that is in fact the correct answer. And how so? Let's just quickly check that. Okay, so let's consider the first option. Okay, so the first option was RUSTYQZVPWX. Okay, so let's see whether that is a valid tour or not. We are starting with R and we are moving in this direction. RUSTYQZVPWX, and we are going back to R. We don't necessarily have to show this. Okay, so we are not needed to write R once again at the end of our representation. Okay, so our representation would be something like RUSTYQZVPWX, and this R at the end is implied. Okay, so this is in fact a valid path representation. Similarly, option C is also a valid path representation where instead of starting from R, we are starting from P and moving in the direction of V. Okay, so basically something like this. Okay, this is what we are doing, and that is option C. Now, why option B is incorrect is that you start from P and then you say that the next in turn is Q, which is incorrect, right? Because P is connected to W and V, but not to Q. Okay, it has to go through either W, X, R, U, S, T, Y and then reach Q, or it has to go through V, Z and then reach Q. Okay, so you cannot directly write that P is connected to Q, so B is incorrect. Similarly, here we have said that in option D, we are given T, Y, Q, Z, V, P and then R. Again, the same problem arises. P and R are not connected directly, right? So P has to go through W and X to reach R, or it has to go the other way around and go through V, Z, Q, Y, T, S, U and then reach R, right? For that reason, B and D are incorrect options, or they are invalid representations. Okay, so some questions in the chat. Uh, in normal condition, path is unidirectional. Am I right or not? Okay, so you are given that the edges are bidirectional. Okay, so you don't need to think about whether it is unidirectional or not. If there is no direction shown, you can assume that it's bidirectional. And also thanks Rocky for addressing that in the chat box as well. Okay, any doubts about this question, or should we move on to the next one? Okay, that's great. So now let's move on to the sixth question, which is another kind of representation. So in the previous question, what we saw was a path representation. We could also use another concept called adjacency representation to represent the same tour. Okay, so now that you have to think about adjacency representations, which of these options would be correct? That's what you have to decide. Okay, so once again, I'll let you think a bit about it, about the options and the adjacency representations, and I'll quickly have some water and then come back and then we can have a discussion. All right. All right. So, yeah, thank you for waiting and sorry for the delay. So, some of you have shared some solutions or your solutions in the chat box, and so a number of you seem to be voting for options A, some of you seem to be voting for options B and D, some of you also seem to be voting for option C, but let's see which of these are correct. Okay, let's now shift to our Jamboard. Let's erase all of this because now we are working with adjacency representations. Okay, so first of all, how many of you are familiar with the concept of indexing and arrays with respect to computer programming? Okay, that's great. So quite a few of you are familiar with it, and that's great. That will help you understand it much easier. And just in the interest of those who might not be familiar, so basically arrays are these kind of data structures where you hold information, and you can imagine it to look something like this. Okay, so you have a, you can say this is a segment of a memory. Okay, and you have each of this whole segment is divided into small segments, and how we access the elements is by indexing each of these segments. Okay, so you call this the 0th index, first index, second index, third index, fourth index, and fifth index, which basically makes it 0 to 5 indices, so 6 segments. Okay, and then you can hold different kinds of information in that. You can, let's say you have A here, B here, D here, F here, let's say J here, and K here, anything. Okay, and let's say you call this array as capital A, right? So if you had to access, let's say, the third index or the fourth segment, because you are starting your indexing from 0, so this will basically return the value stored in this particular segment. Similarly, A0 would return A. Okay, so this is the basic idea behind arrays and indexing, and how that is going to be applicable for our adjacency representation is what we are going to see now. So what we are going to do first is we are going to list all these nodes in alphabetical order. Okay, so let's do that. P, Q, R, S, T, U, V, W, X, Y, and Z. Okay, sorry about that. Now let's write down one of the solutions. Okay, so let's write down the second solution first, which is WZU. Let me write that. WZU TYSP TYSP XRQV XRQV. Okay, and let's write down another solution, which is the last option, VYXU. Let me use a different color for this. VY, sorry about that. VYXU SRZP WT and Q. Okay, so let's do one thing. Let's call this alphabetical arrangement of the nodes as a reference. Okay, and let's use this as our index. Okay, like we saw in the concept of arrays, there was one index, right? So let's use the concept of indices, where each of these indices is marked by this alphabetical listing of the nodes. Now, corresponding to the graph, let's consider the first index. Okay, what is that? That is P. Okay, so we are considering P. Now, which of these nodes are adjacent to P? Okay, so if any one of you is unfamiliar with the concept of adjacency, if we have a graph where a node X is connected to another node Y and another node Z, and let's say there is one more node, let's say P, then X is said to be adjacent to P, Y, and Z, right? Which is basically connected through one edge or one hop. Okay, so can anyone tell me which of the nodes are adjacent to P?
WV.
W and V. Yeah, that's great. So this checks out. Okay, so corresponding to V, we can place W in an adjacency representation, we can place V in an adjacency representation. Now let's check corresponding to Q. Corresponding to Q, we can place either Y or Z. Okay, so we are placing Y in the second one, we are placing Z in the first one. Okay, this is just based on the option that is given to us. Okay, this is not something that we ourselves are placing, we are just checking whether this can be in this condition or not. Okay, is it a valid adjacency representation or not? Now let's check R. So R needs to have X or U. We have U here, we have X here. Now let's check S. S needs to have U or T. So we have T and U. So till now our solution is valid. Let's check T. T can have S or Y, Y or S. That is also correct. Now let's check U. U can again have R and S. So S and R, which are also correct. Let's check V. V can have P and Z, right? So P and Z, which is again correct. Let's check W. W can have X and P. X here, P here. Let's check X now. X can have R and W. We have R here and W here. Let's check Y. For Y, we can have T and Q. We have Q here and we have T here. And last for Z, we check we can have V and Q. We have V here and we have Q here. So we see that for each of these indices like P, Q, R, S, T, U, V, W, X, Y, Z, the corresponding value in the array or the solution or the tool that is given to us has a proper adjacency, right? So options B, this was our option B and this was our option D. Both options B and D are valid adjacency representations. But if you do this similar process for A or C, you will find that some vertex is there which is not adjacent to the reference indices. Hence, options A and C would be invalid adjacency representations. Let's just take one example, okay? Let's say R. Okay, so the value corresponding to the first index is R in the first solution that is given to us. But you see that R is not adjacent to P. Okay, R is not directly connected to P. So that itself says that the first option A is not a valid adjacency representation. Let's check the answer quickly, and the answer is in fact B and D. Okay. All right then. Any issues about this particular solution? Okay, that's great. Okay, so let's do a quick recap of what we have done till now. Okay, so in the first few questions, we saw how exactly to implement the steps of a genetic algorithm. Okay, to calculate fitness, to do selection, and we had said that we will do a crossover. Okay, so that is still remaining. We'll see that in the coming question. In the next few questions, we introduced ourselves to what a TSP problem is. Okay, in the in this question, the current question and the previous one, we saw what are some possible representations of the solutions that we are going to deal with. Okay, so now we got two representation. One is path representation, one is adjacency representation. There could be other representations also. You can revisit the lecture if Professor Kimani has discussed some other things, or you can just leave it at whatever is there in the lectures. And I'll come back to your question in the chat box. Let me just complete my line of thought. Okay, so we have seen some possible representation of solutions. Now what we are going to do is we are going to do or have a look at how we could do a crossover in case of the particular TSP problem. Okay, so usually how we perform crossover is through this concept called a single point crossover. Okay, suppose you have a binary string something like this 0 1 0 0 1 0 0 1. Okay, so in single point crossover you select one point among these indices randomly. Let's say this point. Okay, and so this is your first parent, this is your second parent, and what you do is to form the children you just select this the left part of the first parent and the right part of the second parent. Okay, so that would give you one child 0 1 0 1, and for the second child you select the left part of the second parent and right part of the first parent 1 0 0 0. Okay, so this is how you do a single point crossover. Okay, so crossover is basically a way to generate new individuals or children from your given individuals which are parents. Okay, so this is basically mimicking the process of DNA replication and reproduction in us humans or any species for that matter. Okay, and that is why this is called a crossover. But this will not apply in the case of TSP problem. Let's say we have something like A, B, P, Q, and then some other tour, let's say P, Q, B, A. Okay, this is some random hypothetical tour. If you do something like a single point crossover here, you will get some children, but that tour might end up being an invalid tour, right? For example, in this particular case, you will get something like ABBA, which is completely invalid because you're not even visiting P and Q in the first place. And similarly, here you got PQ, which is also invalid, right? So single point crossover will not work in case of a TSP problem. So we have to adopt to different strategies of crossover, and we are going to see one such strategy in the coming question. Okay, so okay, maybe that is not the next question. So before moving on to the crossover, let's look at one more representation um, that will make it easier for us to do a crossover basically. Okay, so this is called an ordinal representation uh, of the value. So we saw path representation, right? From one of the previous questions, and we can transform this from this alphabetical string or list to a list of numbers, which is basically called the ordinal representation of a particular path representation. And once we do that, we are going to do the crossover, which I already explained you what that is. And yeah, so I'll give you some time to try to arrive at the ordinal representation while I address some of the questions in the chat box. Okay.
Hello, sir.
Yeah.
Hello, sir.
Yeah.
Sir, what is this greedy heuristic? When I am solving a traveling salesman problem, I'm not understanding what I have to do in the greedy heuristic.
Okay. Uh, let's do one thing. Um,
Yeah.
let's again finish. So there are two questions remaining. Okay. This question 7 and question 8. And after that,
Okay.
I will arrive at what greedy heuristic is. And there was another question about saving heuristic and all that. If
Yes, sir. I cannot understand all those questions.
that's okay. But
Uh,
what I would really recommend moving forward, and I would really emphasize this strongly, then if you want a specific topic to be covered, uh,
okay.
it will be really beneficial if you could post in the discussion forum saying at least I would prefer if you could post it a week before even. Okay, but
Okay.
at
Okay.
least 2 3 days before, post in the discussion forum saying that be uh, I would really like to have this particular topic questions discussed in the next live session so that I can prepare the questions accordingly, right?
Okay.
So
Okay. Sir,
it's
Ritik sir,
okay.
may I tell you? May I ask you something?
Uh,
I understood your thing.
yeah,
बस सिंपल मैं ये बोलूँ that suppose this is the map, ये ऊपर में जो something is there ना, ऐसे कोई map है suppose, हैं, ठीक है, ये simple एक दो छोटे छोटे देखे यदि आप example देखे यदि if you can explain छोटी सी बस we can understand those things, I think.
that's fine. And
Yes, sir.
I fully believe that you can understand, but I also need to be in touch with the concept to explain it
Yes,
properly,
sir.
right?
So are you in touch with this saving heuristic and greedy heuristic today?
I will see that. We will go through the lectures, and if we have time remaining, the lecture notes, and if I can see that it is something that is explainable in the time remaining, I will do that. But I cannot guarantee that, right? Because see,
Okay.
as I said earlier, all of us are busy, right? So if we could decide on the specific set of topics that you really want to want to focus on, you should post that in the discussion forum, and
So
then
the
we
next
can
this
have
time I
it
will do that.
accordingly.
And sir, one more thing, sir. Just say today you have the session is there. So when it will be posted, this session. Once it happened, that means after the assignment date got over, the session was posted. So it was not beneficial in that way if we do not join the session.
Yeah,
Yes. Yes.
I do understand that, and I really appreciate your concern for that. But as I had mentioned in the previous live session, that was a technical issue, not something really in my hand. So,
Okay.
yeah, but what I usually try to do is get the recording uploaded by the next day maximum. Okay, so
Yes.
it's still my aim would be to get the recording up by tomorrow, so that you still have one day to go through it if you want to before submitting the assignment on Wednesday midnight.
Yes.
Okay,
And sir, one more thing, sir.
and
One more thing.
yeah, just
One more thing, sir.
let me just complete my thought.
Okay.
If
Okay.
in case there is any issue like that happening again in the future, as in whereas the recording is not getting uploaded on time, although I'll try my best to do that,
Okay.
the lecture slides, not the lecture slides, the question slides that we discuss in the problem solving session, they are always uploaded ahead of the live sessions. Okay, so even if there is an issue with the recording, the presentation and the slides will always be there. Also, the same questions or similar questions we have discussed in the previous run of the course as well, where we had live sessions. So if there is a real necessity, you can even visit the playlist in the same YouTube channel,
Okay.
which covers the questions for similar topics in the previous year's live sessions. Okay, yeah, coming back to your question. Yeah, please go ahead.
Sir, what is happening? This, sir, I forgot. The thing.
Okay,
I forgot.
you can take your time, and if it comes back to you, please feel free to
सर वन मोर थिंग सर, सेविंग्स टूर जो है, सेविंग्स टूर एक बार आप देख के सर थोड़ा 1-2 मिनट आप देख सकते हैं सर, देख के देखिए तो इज इट पॉसिबल टू सॉल्व
I will
सेविंग्स टूर?
I will try. So if I remember correctly, you are Rajesh, right?
यस सर, राजेश सर।
Okay, yeah. Thanks for bringing it up, Rajesh.
रिमेंबर मी?
And
यस
yeah,
सर।
yeah, of course. So let's since there are only two questions left, let's quickly
ओके ओके
complete
सर,
that in the
डन
interest of
डन डन
people who might not want to discuss the other things. And then if we have
ओके
time, we'll figure it out.
ओके ओके डन डन सर, प्लीज गो अहेड सर, प्लीज सर, प्लीज।
Okay,
ओके, थैंक यू
thank
सर,
you.
थैंक यू।
Okay, so Dr. Ashwini had asked, what is the need of adjacency representation over tour representation? When is it necessary? So in certain situations, you would prefer certain representations over other representations. There could be computational restrictions, there could be space restrictions, memory restrictions. So many in some cases, basically storing the adjacencies values would be more computationally efficient than storing whole tours and whole representations. Okay, so here we are dealing with very small toy problems. Let's say you have tens of thousands of even lakhs of nodes in a graph. You would want to store your solutions or your candidate solutions in a way that is not consuming too much of memory, and when you are going through the steps of the algorithm to arrive at your final optimal solution, you would want something the steps to be basically more efficient in terms of complexity and time, space and time complexity basically. So there are some of these restrictions or preferences even for problems for different users, which is when you could prefer one representation over another. So that is the whole thing, and I hope that addresses your question. Okay, so yeah, the recording uploaded, I've already addressed this n number of times, so I will not go through that again. And ordinal representations, so some of you have already shared the answer. Let's quickly go through the solution before time runs out. Okay, so let me write that down. Okay, so the solution that we were given is RUST YQZV PWX. Okay, and once again, let's write down the alphabetical order. Okay, so let's name these as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay, so what we are going to do is we are going to look at the first node over here, which is R. Okay, and look at what is the value of R over here, which is 3, right? So we'll write 3. So 3 is the corresponding value for R. Okay, now we will move on to the next node, but before doing that, we will have to modify our numbering system. Okay, so once we have already gone through R, we will not consider that, right? So when we will have 1 is P, 2 is Q, and 3 will be assigned to S now. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, now let's consider what is the index of U. So index of U is, or value of U is 5, right? Over here. So we write that down and we remove U. Okay, and once again we modify our um, numbering system. So now we have 1, 2, 3, 4, 5. We will now have 5, 6, 7, 8, and 9. And now we will move to S. Now what is the position of S? S has 3. So we will write 3 for S, then remove S. And again we have to modify our numbering system. Okay, so now we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now T has 3, so we write 3 again and we remove T and we proceed in a similar manner. Okay, and we keep doing that um, until we arrive at the ordinal representation of this particular path representation. Okay, so I've listed down the solution over here. I'll zoom in a bit and I'll let you go through it and let me know if this seems sensible to you. Okay, so the final solution would be 3533 6252 111. That is our ordinal representation. Okay, this is the solution. You can have a look at it while I will address some of the questions. Okay, so what is the difference between a problem solving agent and candidate solution? Um, so I'm basing this off of my intuition. Okay, so I would recommend that you revisit the lecture notes and see if there is some technicality involved over here that Professor Kemani has discussed. Okay, in that case, if that is the case, follow whatever Professor Kemani had said. But based on my intuition, what I can say is the candidate solution is, let's say in this particular problem, in a TSP problem, it would be one possible tour. Okay, one of the possible valid tours that may or may not have give us the optimal cost. Okay, so usually we also have a cost associated with a tour, right? And we will see in the coming weeks, we will see some of the algorithms that don't just focus on finding a tour that covers all vertices, but also find a tour that covers all the vertices with a minimum possible cost associated. Okay, so the candidate solution would basically be all the sets of valid tours in that case. And a problem solving agent is what I can think of might refer to the kind of algorithm or kind of solution that you are adopting. Okay, so it could be something like a genetic algorithm, it could be something like this ant based algorithm that is also discussed in week 4. It could be something like a taboo search, it could be something like simulated annealing. Okay, that is what I can think of. But yeah, as I said, once again, revisit the lecture by Professor Khemani, and if he has stated something technical about these two terms of about a problem solving agent and a candidate solution, then follow that whatever is said in the lecture. Okay, and okay, so once again, to tell how to access the recordings, just go to the Swayam portal, go to the section called problem solving session recording. If you go there, that will lead you to a link to an Excel spreadsheet that will have all the links to all recordings, all YouTube channel, and all the drive folders containing the slides. Okay, yeah. So there was another question that I had forgotten to address, which is if adjacency will have loops, will it choose the next node randomly? Um, I'm not sure how adjacency will have loops over here. So a node can be connected to any n number of nodes, right? And we just have to check whether they are adjacent or not. If there are loops in the possible solution that you're trying to examine, that itself means that it is not a valid solution. Because in our TSP problem, we don't want loops. We only want one tour that covers all vertices. Okay. So if there is a loop, then that is not a valid representation. Or if there are subcycles that are part of a bigger loop, that is another case. Okay, that there could be cycles in between our tour. That is a different case. I am not sure if I addressed your question, but uh, feel free to let me know if it is not clear. Okay, so any doubts about this ordinal representation?
So, what is the need of ordinal representation?
So ordinal
What is the advantage
representation.
of this actually?
Uh-huh.
Because this tool representation has some drawbacks. That's
Mm-hmm.
why this ordinal representation is.
Yeah, so basically, do you remember the point about our that I made about a single point crossover not being possible in case of our path and adjacency representations? Uh, if we convert our path representation to an ordinal representation, doing a single point crossover would be allowed or feasible. That is one advantage that we want, that if you want to adopt that, you could switch to ordinal representation. So basically, this existence of this different representation is indicative of different requirements based on different users and different problem statements. Okay, so that is the only reason. And
Yeah, I got it.
okay, and
One more thing. One. Okay.
yeah,
Uh, the nearest neighbor and the greedy heuristic already discussed in the last year sessions, but that is savings heuristic is not discussed.
okay, then uh, it doesn't look like we'll have time today. And once again, I'm sorry about that. But
What is
yeah,
the idea? Can you-
sorry.
Because in the lectures also, what is the idea behind savings heuristic?
Yeah, so once again, I need to go through it myself to be able to tell you properly. So I'll be
Can you
honest
please
about that.
answer in forum?
Yeah, you can always post it in the discussion forum, and Bhaskaran sir will for sure address that. And same goes to
This is not
Rajesh's.
discussed in the lectures also actually.
It's not discussed in the lectures.
Yeah.
Okay, then you should bring that up in the discussion forum for sure. If it is not discussed in the lectures and it is asked in the assignments.
Okay. Thank you.
Yeah, and same applies to your question as well, Rajesh. Uh, it doesn't look like we'll have time today. But yeah, you are 100% encouraged to post your doubt in the discussion forum. Okay, yeah, coming back to Rocky's question, suppose the path is QPRST. Okay, uh, QPRST. Okay, this is a random path you are suggesting. Okay, QPRST, and we write PQSRT. It might create a loop, right? So, what will be the next move? Um, this is in reference to a hypothetical graph or this graph that we were discussing. Um, hypothetical. Okay, so let us do one thing. Okay, maybe you can create that hypothetical graph. Okay, and write down your exact problem, and you can email that to me or you can post it in the discussion forum. Okay, and let's take this offline so that it doesn't consume more of today's time, because I also don't want to extend the time limit we have. Okay, and because mostly because I'm not able to understand your question properly, so maybe if we discuss it offline, I'll be able to give some more time to it. Okay. Okay, so to address your question, in candidate population, probability is coming more than one. That is not possible. Okay, probability can never be greater than one. So if that is the case, then there is something wrong with the um, calculation part of it. The basic axiom of probability is that it has to be a number between 0 and 1. So it can never be greater than 1 or less than 0. Okay. And once again, a general advice, if there is something that you feel that has not been discussed in the lecture videos and um, that is it is being asked in the assignment, please bring that up in the discussion forum. Email ID. So email ID you can post it. So I would prefer you post it in the discussion forum, because that way others will also be able to see it. Okay. Otherwise it will be confined to just me and you. Post it in the discussion forum and make sure you write live session or problem solving session in the heading so I can notice it more clearly. Okay. I hope there are no doubts in the ordinal representation. Now let's quickly move on to the last question for today, which is crossover, the final point that I have been trying to arrive at all this while. So there are different ways to do crossover. Professor Kimani also would have discussed different ways. Here we are going to do one specific type of crossover, which is order crossover. Okay, so you are given these two parents. Okay, and what this blue part suggests in the middle is that this part, the blue part, will be carry forwarded directly to the child. Okay, so let me just write that down quickly. Let me just erase this to make it easier. Okay, so the first one was RUSTYQZV. So it is the solution that I've already written over here. This is the first parent. Let's write down the second parent. That is UXVW. So UXVWQT RPSYZ. RPSYZ. And we are given that this is the window that we have to carry forward directly to the next generation or the child generation. Okay, so we write one of the children as, so you see there are three blanks that we need to fill to the right of the window and to the left of the window. So we copy T, Y, Q, Z and V directly, and we have three blanks over here that we need to fill and three blanks here that we need to fill. Okay, so what we are going to do, we are going to look at the second parent. Okay, and we are going to cross out all the nodes that have already been covered through this window. Sorry about that. Okay, so we see that T has already been covered. Okay, so we cut that. Y has already been covered, so we cut that. Q has already been covered, so we cut that. Okay, then Z has already been covered, so we cut that, and V has already been covered, so we cut that. Okay, now we look at all the nodes that are remaining. Let me use a different color for that. We have U remaining, we have X remaining, we have W remaining, we have R remaining, we have P remaining, and we have S remaining. Now what we can do is we can simply fill in the blanks in the order that it is left for us. Okay, in this order, left to right. So we simply fill in U, X, W, T, Y, Q, Z, V, R, P and S, and this will make our first child. Similarly, second child, we simply copy this particular window, which is W, Q, T, R and P. Okay, and there are three blanks to the left and three blanks to the right. we see which of them have already been covered. W has been covered, so we cross out W from the first parent. Q has been covered, T has been covered, R has been covered, and P has been covered. Okay, so what we are left with? We are left with U, S, Y, Z, V, X. And that makes our second child. Okay, and this is basically order crossover. So once again, this is the solution written over here, and I've also written the steps over here. And so the credits for this goes to Bhaskaran sir. So it is through his solution that I've taken this particular segment. And yeah, so this is how we perform order crossover, and these are the two children that we arrived at. Okay, so yeah. So that brings us to an end of today's session and also the end of the time that we have for today. Uh, so partially ordered crossover is another possible way to do crossover. Okay, that has been discussed in the lecture, and I would recommend you to revisit the lecture for that. And yeah, as I said earlier, um, uh, yeah, if there's any other thing that you would really want to be discussed in the next live session, please post it in the discussion forum. Otherwise, if you have doubts that you think that can be addressed in the discussion forum itself, that is even better. Ask Bhaskaran sir, and he will for sure address your query. Okay, so thanks everyone for attending, and let's meet next week.
So last question alone.
Yeah, I've
Hello.
just displayed that.
सर
Yeah.
Hello.
हाँ सर, सेविंग्स टूर के बारे में थोड़ा सा डिस्कस हो सकता है सर?
Sorry, Rajesh, we are at a shortage of time, like I mentioned.
Okay.
So maybe not today, but do post it on the discussion forum.
Okay, sir. Okay, sir. Done, sir. Done, sir. Thank you,
Okay.
sir. Thank you. Okay.
So in the order crossover, actually in the we have to place the elements from the second crossover point.
So basically, you have to copy the window as it is, okay, and then for filling in the blanks to the left and right of the window, you use the second parent or the other parent. Okay.
Yeah, that is explained like that in the lecture, but in the textbook was proposed. Okay, it is proposed by Davis. They have given like you have to enter from second crossover point.
Okay, so I am not sure about this textbook that you are referring to, so I cannot
So
comment
the
on that.
textbook.
But I would suggest
Okay.
you follow the method that is being
Yeah,
taught in
for
the
the
lecture.
assignment purpose.
Yeah.
Okay. So that is Iben and Smith.
Okay, that's great.
Okay.
Anyone who is interested can refer to this book as well if they want to. Thanks for that, Dr. Ashwini, and yeah, see you all next week.
Thank